Hey everybody, it's Mr. Ray here with our next lesson in grade 12 Calculus and Vectors. We are working with the Introduction to Vectors unit, and we've learned what vectors are so far. They have both direction and magnitude compared to a scalar that just has a magnitude. We also, in the previous lesson, we learned how to add and subtract two vectors and calculate the direction of the resultant vector and its direction. Today we are looking at multiplying a vector. So this once we combine this with adding and subtracting, we'll have a whole bunch of algebraic operations we can do with vectors. So multiplication of a vector. What do we multiply vectors with? Well, we only multiply vectors with scalars. So we don't multiply vectors with other vectors. We have other operations we're going to learn about. What can we do between two vectors? That'll come later on. But for now, when we multiply vector, we're just multiplying its basically its magnitude. We're not going to change its direction. So we can multiply by any scalar, which can be any real number, positive, negative. So let's look at, remember a scalar just has magnitude only, so it's like just a number. Now a couple of definitions here that are important. This a collinear vector, two vectors u and v are collinear if and only if it's possible to find a non-zero scalar k, so k is a scalar, such that if I multiply one vector, say v, by that scalar, I can create the exact same copy of the other vector u. And obviously those two vectors are going to have to be parallel, otherwise they wouldn't be equal because they have to have the same direction as well as the magnitude. Okay, and it says non-zero because obviously multiply any vector by zero, you get a zero vector, and you could always say, well, you know, I could multiply two vectors by zero and they're the same, but they aren't really collinear if it's a zero scalar. So that's why it says non-zero scalar value. We also have unit vectors. So we're going to be talking about those today as well. So a unit vector has a magnitude of 1. Okay, and we're going to create unit vectors in the examples. Okay, now if we have a k, value of k, which is a scalar, we multiply vector a by that scalar. If the value of k is positive, then the resulting vector ka is going to be in the same direction as a, and the magnitude will be whatever the magnitude of vector a was times k. If k is negative, then if I multiply vector a by k, then it's going to be in the opposite direction. It's going to still be parallel, but it's now moving in the opposite direction, and the magnitude of that vector ka will be again absolute value of whatever k was. So in this case k was negative, so for example if k was negative 3, it'd be 3 times the magnitude of whatever a was. Okay, if two or more vectors are non-zero scalar multiples of the same vector, then all these vectors are collinear. So parallel and collinear. Now, in order to get a unit vector, I know this looks a little confusing here. So it's basically taking the vector x and dividing it by its own magnitude. So 1 over magnitude of x is basically dividing x by its own magnitude. So the result will be a magnitude of 1. And we call this the unit vector. Now, you're going to see, I don't use it that much in these lessons, but if you ever see in your journeys through textbooks or YouTube or whatever websites, if you see anything like this, vector x with a hat on the top instead of a vector symbol, this is equal to a unit vector. So we call this, we would pronounce this x hat. There we go. So I won't use it that much. You're more than welcome to use it. But if you want to refer to something as a unit vector, you can put a hat over, and it's implied that the magnitude of any vector with a hat on the top instead of the vector symbol, the magnitude will always be 1. Okay, and this is just this would be a unit vector in the opposite direction of the vector x, so it would be -1 over x. So the magnitude will still be 1 because it's a unit vector, but the direction will be opposite direction from x, or x hat. Okay, a little exercise here. An airplane is heading due north at 1,000 kilometers per hour. The airplane's velocity is represented by vector v. So you can see vector v here in blue. Its direction is due north, and based on the length, we're saying that's 1,000 kilometers per hour magnitude. Okay, so it says draw the vectors -v, 1/2 v, and -1/2 v, and give an interpretation for each. So if I drew -v, well, that's same magnitude, just opposite direction. So that would be -v, and that would represent, in terms of describing interpretation, since this is due north at 1,000 kilometers per hour, this would be due south at 1,000 kilometers per hour. Okay, so that's -v. If we do 1/2 v, it's going to be the same direction as v, but only half the magnitude. So that could be 1/2 v here. And in terms of interpreting what that is, well, it's the same direction as v, so that would be due north, but the magnitude is half, so that would be 500, sorry, due north and 500 kilometers per hour, half the magnitude of the original vector v. And finally, -1/2 v, well, that's just going to be opposite direction of what we just did. So this time, -1/2 v. So that direction is back to due south again. And again, this time the magnitude is 500 kilometers per hour. Okay, so hopefully you see the impact. Putting a negative sign in will, if your scalar is negative, it's going to change the direction to opposite whatever the original vector was. And if you have a number as part of the scalar multiplier, well, that's just going to multiply the magnitude of the original direction. So the direction of the result will either be same direction or opposite direction. It can't be anything else. Okay. So a few more exercises here. Play around with scalar multiples and incorporate that with some of the other stuff we've already learned. So in this case, we've got vectors x and y are unit vectors. So we know that what that means. It means it has a magnitude of 1, both of them. They make an angle of 30 degrees with each other. So the first part says calculate the value of. So basically we're multiplying vector x by 2, and then we're subtracting vector y. And the vertical lines mean that we want the magnitude of that. And then we want the direction of this. I guess this should be just 2x minus y. Take the magnitude signs off, because you can't have a direction of a magnitude. We want the direction of 2x minus y. Okay, so let's start with a sketch of the situation. So we know that they make an angle of 30 degrees with each other, and they both have the same magnitude of 1. So since there's no real firm direction of these, we just know the relative direction with each other. I'm going to start with x. So I'm going to say x is 1 unit. I guess this would be due east. And then if I drew y, so I'll put x here, and y would be same magnitude, but this would be, the two of them would be 30 degrees to each other. Okay, so that is just x and y together. So what I want to do is turn it into 2x minus y. So I'm going to start with the x again, but this time the magnitude is twice what it used to be. So I'm just going to approximate what that is. So that would be 2x. I'll put that label up here. And then I want to subtract y. So the original y, notice when we did these vectors to get the correct position of the angle, the two angles were positioned tail to tail. So when you talk about vectors making an angle with each other, you always position them tail to tail. Now when I'm combining these vectors, doing 2x minus y, they have to be, I want to put them in head to tail position. So when I draw, I want to subtract y now, so I'm basically going to add negative y to the end of where 2x ends. So negative vector y would be the same magnitude but opposite direction. So try to just do a copy of that with the opposite direction. So that would be negative y, and you can see I'm just really just adding those two together. So the resultant would be this new vector here, which we'll call 2x minus y. And the angle that they make, well, we don't know what it is, and that's one of the things we're going to be tasked to find here is, so that angle theta will tell us the position of vector 2x minus y in relation to the vector x or 2x. Okay, so what we want to do now, so the 30 degrees, where did that end up? Well, you can see that this is 2x and y here, so the 30 degrees is actually here. Okay, so what we want to do now is we want the value of this, so we want the magnitude, so I want to basically determine the length of that side of the triangle. So for this, we're going to use cosine law just like we did previously. So it's going to look a little different. So I want the magnitude, so the magnitude of this side squared, so I write that as magnitude 2x minus y squared is equal to the magnitude of 2x squared plus the magnitude of negative y squared, and then basically minus 2 times these two, so 2x times negative y, and then cosine, so in this case I'm going to use 30 as my reference angle because I want to get that third side across from it, cos 30. Okay, so I can clean this up quite a bit. So I'll keep this right side the same. But I know that the magnitude of x is 1 because they've told us that. So double that vector x, that would have a magnitude of 2. So I can change that 2 squared. I also know the magnitude of y was also 1. So negative y, same magnitude, just different direction. That doesn't matter here. So that would be 1 squared. And then I've got 2. And I've just got these again. So 2 times 2 times 1 times cos 30, which is, I'll put that in here as the exact value, root 3 over 2. Okay, and I can simplify this down. That's 4 plus 1. And then I've got 4 here. So negative 4 root 3 over 2. So that simplifies to 5 minus 2 root 3. And then so don't forget I've got that squared over here. So if I just want the magnitude, 2x minus y is equal to the square root of 5 minus 2 root 3. So that would be the exact value. So if you have a question asking for the exact value of this vector, you would have to put that. Most of the time though, you're not asked for exact, so you would just calculate that, and I'll use my approximately equal symbol here. That would be equal to about 1.24 units. Okay, so that's the magnitude of 2x minus y. The second part of the question wants to know the direction. So I can do that over here. So now that I've got my magnitudes of all three sides, plus I've got my angle 30 over here, I'm going to use sine law. So I'm trying to find theta. So I'll start my equation off as sine theta over the magnitude of the opposite side, which should be 1. Well, I'll just put that in here. Magnitude of negative y is equal to, so the angle that I do know is over here. So I'm going to use that side angle combination. So sine 30 over, and then the magnitude of 2x minus y. So it's still the same usual sine law. I'm just putting magnitudes instead of side names because that's what we have here. So this, we know that the magnitude of negative y is 1. We also know that the magnitude of 2x minus y vector, we just did that, that's 1.24. So theta would be equal to, I don't really have to multiply anything because I have a 1 on the bottom, so that's sine inverse of sine 30 over 1.24. That's equal to approximately 23.8 degrees. And again, you'd look for indications in the question about rounding. There wasn't really any direction here, so we'll be as accurate as we'd like to be. 1 decimal might be overkill, but it's always safe. So therefore, so we've got the magnitude of the 2x minus y, and we've got the direction of it. Now that direction is not like a bearing, it's an angle related to 2x. So now this is how we would word it. 2x minus y has a magnitude of 1.24 units. And a direction of 23.8. Now here's where you have to be careful, because if I'm relating it to where x was, it could be on, on the top side, or counterclockwise to where x is, or clockwise. And for us, it's clockwise. You can see the resultant is clockwise from angle x if I rotated. So I would say 23.8 degrees rotated clockwise to vector x. You could also say vector 2x, but I think it's simpler to do that. Okay, so hopefully that makes sense now that you know how to maybe combine multiplication and adding or subtracting of vectors to come up with resultant vectors. Okay, so let's try this question here. Example 3 says the airplane is flying in the direction north 30 east at an airspeed of 240 kilometers per hour. The velocity vector of the airplane is represented by v. Draw a sketch of negative 1/3 v and state the direction of this vector. Okay, so let's we'll start with the vector they gave us, which is v. So I'm going to put my northeast, south, west grid here. Never hurts to put the direction on the ends, just so you don't mess up. A lot of people mess up east-west because they don't think about it hard enough. So vector v is north, so it starts at the north and rotates 30 degrees east. So basically it's 30 degrees off here. So there's my vector v. This would be 30 degrees there. Okay, so if I have a vector negative 1/3 v, well, the first thing is I know the direction of that will be opposite. So if I was to start drawing it, I know it's going to be going the opposite direction. So in terms of the angle, that 30 degrees, if you remember, this is just opposite angle. The 30 degrees is now down here. Now in terms of the magnitude, this isn't completely straight, I apologize. It'd be 1/3 the length, magnitude of that. So I'll just end it right there and call this negative 1/3 v. State the direction of this vector. So negative 1/3 v has a bearing of, and in this question we can use bearing because we know exactly which direction these vectors are pointed in. It's not relative to each other. So this time we start with south because, well, the vector is off the south. It's 30 degrees west of south. So it would be south 30 degrees west. If you wanted to use a true bearing, you could say, okay, well, that's 180 all the way down to south plus another 30. So you could say, or 210 degrees. So either one is acceptable. Now, if they ask for quadrant bearing, that is this. If they ask for true bearing, you have to put this. If they just ask for bearing, you can use either one or both. Okay, second part of the question says, for the vector 3/2 v, state its direction and magnitude. So I don't think we really have to draw anything here. So 3/2 v would have the exact same direction as v, because remember, scalar multiples will either have the same direction or opposite depending on the sign of the scalar. So in this case, it is the same direction. Now, in terms of the magnitude, well, it's going to be 3/2 times the magnitude of the original vector, or 1.5. So 1.5 times 240 means the velocity. Now, when I say velocity, that includes magnitude and direction, so I can state both things here. So has a velocity of 360 kilometers per hour, and the direction is the same as the original, north 30 east. Okay, so I don't have to break this off. When I say velocity, we know it's a vector. Vector has magnitude and direction, and we've stated both things. Okay, let's do one more example. So, example 4, given that vector u equals 4. Now, I was missing my magnitude symbols here. So it should say magnitude of u is 4, magnitude of v is 5, and the angle between them is 120 degrees. Determine the unit vector in the same direction as u plus v. Okay, so this is where we're going to look at unit vector. We're going to do that at the end. So first of all, we're just going to add u plus v. So I'm going to draw, well, again, this is relative angle to each other. So u is a little bit shorter. So I'll draw that here. Here's vector u. Its magnitude was 4. and vector v, remember the angle between them is 120, so they're going to head off slightly like this, and I got to make this a little bit longer. Okay, I guess that's good enough. So there's vector v, and the angle between them is 120. Notice again I'm putting them tail to tail to show the relative position to each other. Now what I want is u plus v. So here's where I can use my parallelogram again. I can either copy u up here. So here's a copy of u, or I could take a copy of v up here. Either way, I've got u plus v here, so remember vector v goes this way, vector u goes that way. So I could either go u plus v or v plus u, but I end up at the same end position. So I've got my resultant vector here. And I could call that r. I could be more precise. U plus v is the dark vector here. Now, again, the 120, that doesn't get cut down the middle necessarily. We can't really use that here, but what we can use, since it's a parallelogram, we know we know the adjacent angles are going to add up to 180. Another way to think about it is the opposite angles are the same. So I've got 120, 120, and these two are the same, so I've got basically 360 degrees left between the two of them. So this angle here will be, 180 minus 120, so this would be 60. Yeah, so I had 120 to share between these guys, because it's 360 total. So that 120, 120, and then half of 120 here. So there's the triangle I can work with to come up with my magnitude of u plus v. So again, I'm going to use cosine law. So similar to the first question we did, magnitude of u plus v squared, okay, is equal to, now we know the magnitudes of u and v, but I'll put them here to start off with. Magnitude of u squared plus magnitude of v squared minus 2 magnitude of u times magnitude of v times cosine 60. Okay, so I've got u is 4, so that's 4 squared plus 5 squared minus 2 times 4 times 5 times cos 60. If I do all that, it works out to 21 exactly, because I believe that's 0.5. And then if I want to get the magnitude, I got to take the square root. So magnitude of u plus v is equal to the square root of 21 units. And that, of course, that's exact. We'll leave it like that because we're going to be using this in our unit vector. So you never round when you're calculating the magnitude for your unit vector. So I know the I know the overall direction of u plus v, and I know the magnitude is root 21. So what I want when I'm talking about creating a unit vector in the same direction as u plus v, it's going to be, I want this to be exactly 1 unit long in the same direction. So how do I get the new vector? Well, I have to take u plus v. So let me write this out. So unit vector in same direction as u plus v. Okay, so what we're going to do is we're going to take the magnitude of u plus v, and basically to get this back to a magnitude of 1, we basically multiply by the reciprocal of this, or in other words, divide by this. So we always have this scalar multiple out front, which is 1 over the magnitude of this vector. So it's going to be 1 over root 21, and then multiplied by u plus v. So we'll just leave it like that. We're not actually calculating any direction for this. We're just saying, what's the scalar multiple of u plus v that gives us a unit vector. So it's basically 1 over root 21 times whatever u plus v was. Okay, and if we wanted to expand this, we could. 1 over root 21 u plus 1 over root 21 v. Okay, so that's anytime we want to get a unit vector, we have to calculate the magnitude of the resultant, and then we make that into a reciprocal scalar to create a magnitude of 1. Okay, so that's it for this lesson. Got some homework questions from the textbook for you to try out, and hopefully that made sense, and we'll see you on the next lesson where we're going to dive into some properties of vectors. Have a great day and take care.